And today I want to share some of my notes on knot theory. So for the past few months, I've been studying knot theory using this book, Knots, Links, Braids, and Three Manifolds, an introduction to the new invariants in low-dimensional topology by Prasolov and Sossinsky. I really love this book so far because it's super visual. They include these really beautiful hand-drawn diagrams. And also, the way it's written, they include exercises and solutions in the back. And before I get into the math of these notes, I'll explain the process for creating them. I use this blue notebook that I really love. It's very thin, durable, flexible. It's 96 pages, 24 by 32, so pretty large area for writing. I got it from France. And I really just love the graph paper too, because it helps you, the lined paper, because it helps you orient your writing and your diagrams as well. And then for writing, oh yeah, I have so many, I really love these blue notebooks. I don't think I could take notes just as well on any other notebook. And then for writing, I have a very small handwriting. I find it neater. And to do this, I sharpen a pencil until it's very pointy, and yeah, I just write. And then for the diagrams, what I do is I do a tiny sketch, and when I'm happy with the result, I'll take a very inky pen and just trace over my sketch. I really like how the black kind of pops out from the text. This is a technique that I didn't have the last time I did my notes, but I really like the diagrams here. Yeah, knot theory and low-dimensional topology in general, I think it's the best note-taking subject just because of how visual it is. So very fun to do all the drawings. Yeah, that's why I wanted to share these notes with you. So yeah, let's get into the math. So the first thing they do is introduce a knot. And what is a knot? Well, here are some examples of knots. You have the unknot, the trefoil, and the figure-8 knot. And what all of these are basically are just a piece of string that you knot in any fashion, and then glue the ends of those strings back. So it's kind of like a circle that knots itself. So here's the unknot, which is just a circle, and here's a trefoil, a slightly more complicated knot. I think this is the knot what you get when you tie your shoes, and then so on and so forth. So how can we represent these knots? Well, it's just overlapping and underlapping, right, on a projection on a 2D surface, in this case, the paper. So just to make sure that you can represent a knot this way, you have to be careful about, you can always avoid these three-way intersections, so you have a clean over-underlapping. And then you move on to these polygonal links and knots, which help you formalize the smooth knots you see here, the differentiable ones. Here are some plane isotopies, these moves that you can do with these knots. You know how you can kind of squish your shoelace in any form? This is basically that. And then a wild knot. You can see that these knots look very different from a wild knot. It has some sort of infinite spiral and descent. Very cool. I would want to learn more about these later. And then what they do is they prove a few theorems about knots. That you have a binary operation between knots. This is very important. And then you can prove that this binary operation is commutative. And then you can prove that connected summing does not unknot. So there's a way in which you can think of knots as a monoid, right? You have a binary operation and it's commutative. So that's page 1. And now page 2. Here it's all about the Riedmeister moves. How can you get from one knot to the same knot just by squishing and moving, overlapping, underlapping pieces under itself. You can actually get from one same knot to any other same knot using just these three moves, and then plane isotopies as well. And this is the proof for why you can do this. And then they give some diagrams here. Here are some diagrams of various knots. The trefoil right here, and the figure-8 knot on the bottom. Here are some knots, the Whitehead links, and then here's a trefoil, and it's actually not equal to its evil twin, the amphichiral, so it's not amphichiral. yeah, that's page 2. Now, page 3 is when they introduce the Skine relations. So I think you can do some arithmetic with knots using these 3, maybe recursive identities. You can just simplify, 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 and you get this cool kind of arithmetic with knots. Oh, there's a piece right there. Yeah, very, very cool. That's page 3, I think. And now we begin defining the invariant. So we have this equation, that's I think the main equation here, the Reich number, and you're able to define the Kaufman and later Jones polynomial, which are provably invariant under the Reidemeister move. So these polynomials are the first knot invariants that we're introduced to in the book. Super powerful tool. Yeah, that is page 4. Now, the next page, this was a really awesome page to draw. It's just a tabulation of the prime knots with 7 crossings or less. Yeah, so before we get into that, here are 2 knots for computing the Jones polynomial. And then here are all the prime knots, starting from the trefoil, I think the smallest of all of them. Yeah, very, here again, I just traced with pencil and then colored over with ink. These are really, really fun to draw. And then here is a prime and non-alternating knot. So that's a very special knot. Yeah, here are some equations about, I guess, the invariants. And then here are different knots with identical Jones polynomial. And this is the big problem in knot theory. Given 2 knots, how can you ensure that they're not the same knot, or that they are different? And although invariants can be helpful, they're not perfect, and this is an example of this flaw. Alright. The next page, it's more on these polynomial invariants. So you have the Conway polynomial, the Jones polynomial, the Alexander polynomial, and also the Homfly polynomial. So these are all invariants. They work slightly well, but not all the time, and that's the big problem. And then what's this diagram? Crossing changes, leaving the thing intact. Okay, that's the other page. I think now it's the Gauss diagrams. So it's a way of representing knots as chords on a circle. It's a cool system. I don't remember too much about this, but I can always go back and review. And then here they introduce braid theory. So not knots, but braids, where you connect. It's almost like a permutation where you connect braids overlapping, underlapping on 2 ends. And these, unlike the knots, which are only a monoid, these form a group. So very, very special property, super powerful. There's operations between braids, and yeah, you can do a lot of things with them. Super interesting. But I prefer knots in that they don't have such a easy structure. There's more work to do. There's more work you have to put in for knots. And then now the text gets into manifolds, 3 manifolds, and I think a little bit of 4 manifolds, low-dimensional topology. So you start off with what is a manifold, and then handle bodies. This would be an example of a handle body. Torus would also be another example. And then they discuss Heegaard splitting, which is the presentation of a manifold as the union or some gluing of 2 other manifolds. So you have a neighborhood around a point X. This is why it forms a manifold. And this is the proof that any orientable 3 manifold can be obtained, or has a representation as a Heegaard splitting. Very cool proof. The next page, oh yeah, here's a torus with its coordinate system. And I think this was all about Heegaard splittings involving tori. And then you can also think about knots kind of circling around the torus knots, I think. So this is the representation of trefoils on a torus. Yeah. And they prove that the space of cubic polynomials without multiple is homotopy equivalent to the complement. The sphere minus the trefoil knot. Sorry, my brother is calling me right now. Alright, yeah. Also very nice topological proof here. Okay, this is the next page. So I think these are Heegard skeletons of manifolds. And yeah, I love doing these topological diagrams as well. The shading is very fun. Yeah, so this is the canonical system of meridians. And then another cutting M1 into a 3-disk. And then a Heegard splitting corresponding to the Heegard diagram. Very cool stuff. Oh, and then now it's all about lens spaces. So you have points on the boundary of the 3-cell, identifying the boundary of a lens. And they don't discuss how this is related to knots, but I guess it also it'll be used later on in all of this low-dimensional topology, and I think in like surgeries later on. So here's a Heegard diagram of one of these lens spaces. Yeah. The next thing is den twists. So a den twist is a really cool operation. You basically take some handle body, and then you cut it, karate chop it right here, and then you take one end and twist it, hence the name den twist, and then glue it back together. So if you do this on a torus, karate chop that, and then twist, you can see how the meridians of the torus kind of change. They have this, it goes back, it kind of twists a little bit. So there's a theorem that any orientable 3-manifold can be obtained by a den surgery, or also it can be obtained by cutting out some tori from the 3-sphere and then kind of gluing it, pasting it back in, but differently. So this is a homeomorphism of some manifold minus a tubular neighborhood induced by a twist. Yeah, I think this is a very powerful tool in describing 3-manifolds because you can construct any 3-manifold by this operation by cutting out a knot, and the manifold obtained and the knot that was used to obtain that manifold share some similar properties that you can exploit. Oh, and this is where my notes begin to stop. You can see here I have one of my sketches that I yet have to finish and overline. But I think I have some more stuff on the next page. Yeah. So here are 2 non-isotopic links with homeomorphic complements. And then more of the twisty stuff right here. Also some stuff on the Euler characteristic. And then I think I ended on a corollary called a surgery operation. Yeah, so just when things were getting very, very interesting, I'm creating this video a little bit to motivate myself to get back in this note-taking. So yeah, those are my notes, and I'll run through them one more time. So this is page 1, the introduction. The second page, Reidemeister moves. Third page, some of the arithmetic with knots. And then the polynomial invariants, the prime knots. Some more arithmetic and invariants. Gauss chord diagrams. Braid theory. And then manifolds, Heegard splittings. Trefoil on a torus. Some more topology stuff. More topology stuff. Heegard skeletons. And then lens spaces. And then den twists. And just beginning all the surgery stuff. Alright. Here's the book again. And I hope you enjoyed this video. Thanks.